Hello everyone. So let's continue what we did last time, where our goal, if you remember, was to use second moment method to derive results, and in particular, we want to show that the random graph G of n and p contains a triangle if p is large enough, almost surely, and it would not contain a triangle almost surely if p is small enough. So there is a threshold function that determines this, whether the random graph almost surely does contain or does not contain a triangle. So we looked at some basic results from probability last time, second moment variance, covariance. Now another thing that we need for this topic is a big O, small o, capital theta notation, where maybe you have seen it before, but let me do a quick review about that. So let's start with big O notation. So we call definition, let's say f and g be functions on R. We say f is or belongs to OG, capital O of G, if there exists, let's say, constant C and let's say x0 in R, such that absolute value f of x is less than equal to C times absolute value g of x for x bigger than equal to x naught. So if f is at most a multiple constant of g, then we say f is or belongs to OG. So these big O notation, small o notation, these are the concepts that are related to many fields of mathematics. For example, number theory, there's lots of applications of these notations. But we will also use it in this course a lot as well. So this is the meaning of big O notation. So let's look at a simple example. For example, let's say f of x equals x squared plus x plus 2. Then we can say f is O x squared. So basically, this capital big O notation determines the asymptotic behavior of f. That, if x is large, how does f behave, or is dominated basically by which function at least. Okay, so here we are saying that this f is dominated by a constant times x squared if x is large enough, according to the definition of big O. So, well, that's obviously true, the reason is, I can say that, f of x equals x squared plus x plus 1 is less than equal to 3x squared, right? For x bigger than equal to 1. Because, if x is bigger than equal to 1, x is less than equal to x squared. 1 is also less than equal to x squared. So x squared plus x plus 1 is less than equal to 3x squared. So our constant c is 3 and our x0 is 1, right? This is the definition. Now, if x is bigger than 1, of course, absolute value f of x is going to be same as f of x itself. If x is bigger than 1, everything is positive. X squared and x and 1 are all, or 2, I said, plus 2. So then I need x squared. So this is less than equal to x squared plus x squared plus, let's say x squared, which is 3x squared. This time I can say for x bigger than or equal to, let's say, 2. If x is bigger than or equal to 2, 2 is less than x squared, and x is less than x squared less than or equal to x squared itself. And so absolute value f, which is x squared plus x plus 2, is less than or equal to 3x squared. Okay. All right. So another notation is small o notation. We say f is small o of g if limit absolute value f of x over absolute value g of x as x goes to infinity is 0. So for example, let's say we can say f of x equals x squared is small o x cubed, right? And the reason is limit x squared over x cubed as x goes to infinity. Again, you can say absolute value, but again, of course, absolute value x squared is same as x squared. Absolute value x cubed is same as x cubed when x goes to infinity. So this is 0. Okay. And another notation is we say f is in capital omega of g if f does not belong to small o of g. So capital omega is the negation of small o. Well, this is one way to define it, but what is the equivalent way to define this? When can I say that f is not small, does not belong to small o of g? If limit absolute value f over g is not 0. So if limit absolute value f over g is something positive, of course, that's one of the possibilities where I can say f does not belong to small o of g, and therefore it's capital omega of g. And another possibility is that, let's say, the limit absolute value f over absolute value g does not exist. And in that case, still, I can say that lim sup of f over g is positive. So this is equivalent with the note f to omega capital omega of g if and only if lim sup of absolute value f of x over absolute value g of x as x goes to infinity is positive. But here I don't want to go into too much details of lim sup and what it means. I've probably seen it in other courses such as basic analysis course, but just to let you know and do a very quick review, if limit absolute value f over g, well, we know that if it exists, limit absolute value f over absolute value g, because absolute value f over absolute value g is non-negative. If the limit exists, it's either 0 or positive, or a positive number. Now, because I want this to be negation of small o, so if limit absolute value f over absolute value g is 0, then f belongs to small o. So one way for limit absolute value f over absolute value g to be not 0 is that it can exist and it can be a positive number. In that case, it won't be 0, of course. And if limit exists and is positive, in that case, lim sup will be also positive. Please recall from a basic analysis course that if limit exists, then lim sup and lim if, both of them exist and are equal to the same number as the limit itself. So in that case, lim sup exists and is positive because limit is positive. Another case, another possibility in which I can say limit absolute value f over absolute value g is not zero is that limit would not exist. If limit absolute value f over absolute value g does not exist, that means lim inf and lim sup are not equal to each other. And this would imply that lim sup has to be positive. Why? Because if lim sup is not positive, it has to be zero. If lim sup is zero, lim inf will be also zero because lim inf is always less than or equal to lim sup, and absolute value f over absolute value g is a non-negative function. So lim inf cannot be less than zero. So if lim sup is zero, lim inf has to be zero because on one hand, it cannot be negative. On the other hand, it has to be less than or equal to lim sup. And in that case, lim sup and lim inf, both of them will be equal and limit would exist. So if I assume limit does not exist, that would imply that lim sup has to be positive. And lim inf will be some number strictly less than lim sup. And of course, greater than or equal to zero. Okay, so anyways, this was a basically quick reasoning about why f does not belong to small o of g is equivalent with saying that lim sup absolute value f over absolute value g is positive. But maybe in practice, it's easier to use this one. If you want to check f belongs to capital O of g or no, just consider limit absolute value f over absolute value g. If it's zero, then f belongs to small o of g. If it's not zero or does not exist, then that means f does not belong to small o of g, and this means f belongs to capital omega of g. So for example, let's say f of x equals, again, x squared plus x plus 1 belongs to small capital omega of x squared, because limit x squared plus x plus 1 over x squared, x goes to infinity, is 1, which is not equal to 0. So that means f does not belong to O, small o of x squared, and that means f belongs to capital omega of x squared. Okay, and the last notation that we need, f belongs to capital theta of g, capital theta of g, if, when can I say belongs to capital theta of g, if f belongs to capital O of g and f belongs to capital omega of g. So capital theta, basically capital theta intuitively determines the asymptotic behavior of f. How does f behave? Does it behave like x squared, or does it behave like x cubed, or what? So for example, see, if I say f of x equals, again, x squared plus x plus 1, this belongs to capital theta of x squared. Intuitively, x squared plus x plus 1 behaves like x squared as x goes to infinity. The asymptotic behavior, right? And this is true because we check that f belongs to capital O of x squared and f belongs to capital omega of x squared. Or another example, let's say f of x again equals x squared plus x plus 1 does not belong to capital theta of x cubed. X squared plus x plus 1 does not behave like x cubed, so it should not be in capital theta of x cubed. Why is that true? Because, well, x squared plus x plus 1 belongs to capital O of x cubed, because absolute value f is less than or equal to some constant times x cubed. So that condition holds. But f does not belong to capital omega of x cubed, right? Because x squared plus x plus 1 belong to small o of x cubed, since limit x squared plus x plus 1 over x cubed, x goes to infinity is 0. So this limit of this fraction is 0. So this means this belongs to small o of x cubed, and that means this does not belong to capital omega of x cubed, and this means x squared plus x plus 1 does not belong to capital theta of x cubed. Okay. Okay, so this was about big O, small o, big theta, and omega notation that we're gonna need today. And another concept that we need today is threshold function. Remember, I told you that, you know, when we consider random graphs, g of n and p, if p is smaller than some threshold, then it would not contain a triangle. Bigger than some threshold, it would contain a triangle. Of course, almost surely. Now, therefore, we need a concept for threshold function, where it determines, you know, the border, basically, that less than that it would not contain, bigger than that it would contain. So definition, a function R from N to R is called a threshold function if for a monotone graph property A we have, so two things. A, if P of N is equal to small o of R of N, then probability that A holds, the property A holds for G of N and P of N is equal to 0 when you take the limit as N goes to infinity. Part B, if R of N is small o of P of N, then and limit P of A holds for G of N and P of N is equal to 1 as N goes to infinity. And here we are mentioning about a monotone graph property A. What does that mean? So a property A is called monotone if for any two graphs G and H with vertices of H is equal to vertices of G and edges of H subsets of edges of G, and for any two graphs G and H with this, and H having property A, G also has property. Okay, there are a few things here that are considered to be new concept. One is the concept of monotone property A. So monotone property for graphs, monotone property means if you have two graphs with same vertices, one of them, first one, the edges of first one subset of second one. If the first one with smaller edges has that property, the one with bigger sets of edges and same vertices must also have that property. So in particular, in our context, we want to look at property A means having a triangle in our graph. So if you have two graphs with same vertices and the first one, the edges of first one is subset of second. Now if the first one contains a triangle, but for sure the second one, which has the edges of the first one plus possibly some more edges, definitely also contains a triangle. So having a triangle is a monotone property. Okay, so that's one thing. Another thing is threshold function. Now, what does this mean? You know, this looks a little bit complicated. P of n, small o of R of n, then limit this probability is 0, R of n, small of P of n, limit this probability is 1. Now, let me explain this with our context, which is, again, as I said, having a triangle in the random graphs. Probability of having triangle in random graphs. So, theorem, I'll explain threshold function through this theorem. Consider the random graph G of n and p. Okay, random graph with n vertices and edge probability p. Okay, so if, now I want to state two things. If p of n, if p is equal to small o of 1 over n, then limit probability that G of n and p contains at least one triangle as n goes to infinity. This is 0. And part B, if 1 over n is small o of p, then limit probability G of n and p that contains at least one triangle is 1. Again, as n goes to infinity. In other words, R of n equals 1 over n is the threshold function for having a triangle in the random graph G of n and p. Okay, So there are two things. As I promised you earlier, we said that when you consider the random graph G of n and P, if P is smaller than some threshold, it would not contain. But if P is small, it means that, you know, the probability of appearing one edge is very small. So number of edges would be, expected number of edges would be small, and therefore probably our graph would not contain a triangle. And similarly, if P is bigger than some threshold, it would contain a triangle. So in particular, we are saying that if number P is much smaller than 1 over n, small o of 1 over n means what? Means limit P over 1 over n is 0. So P is much smaller than 1 over n. Then the probability that our random graph contains at least one triangle is 0. So in our notation and terminology, this means that asymptotically, almost surely G of n and P contains no triangle. Almost surely because probability is 0, asymptotically because n goes to infinity. And also if the second part says if 1 over n is much smaller than P. The first part says if P is much smaller than 1 over n, the probability is much smaller than 1 over n, probability of appearing one edge, then almost surely the graph contains no triangle as n goes to infinity. Second part says if 1 over n is much smaller than P, then almost surely G of n and P contains at least one triangle. And contains at least one triangle. Again, almost surely because it happens with probability 1 as n goes to infinity. Okay, so this means this exactly matches the definition we gave for threshold function. If P is much smaller than R of n, then probability that A holds is 0 as n goes to infinity. If R is much smaller than P, the probability that A holds is 1. Okay, so if we prove these two things, it matches the definition of threshold function. And this means for having a triangle, the threshold function is 1 over n. And when we say 1 over n, of course, you can consider, let's say, c over n, because if this happens for, you know, if, for example, p is O1 over n, it's also small o2 over n, right? Or 5 over n. So, of course, we're talking about up to a constant. Okay. So there are two things that we have to prove here. The proof. Okay. So first part A, what do we want to do? So given G of n and P with and P equals small o of 1 over n, we want to show that probability that G of n and P contains at least one triangle is 0 as n goes to infinity. Okay, now first of all, I want to ask how many possible triangles can we have in G of n and P? So let's start with that. So note that G of n and P can possibly contain and choose 3, right, triangles. G of n and P contains n vertices, so any 3 vertices that I choose, possibly it can form a triangle, if the triangle can be formed there. I can have possibly one triangle there. So in total, I can have and choose 3 triangles. So let's say A1, A2, all the way to A and choose 3 be events of having a triangle with any of and choose 3 options of vertices. So for example, vertex 1, 2, 3, I can have a triangle there, right? Possibly. A1, I'm considering to be the event that I have a triangle with vertices 1, 2, 3. A2, the event that I have a triangle with vertices, for example, I don't know, 1, 2, 4. So in total, I have n choose 3 events, A1, A2, all the way to A sub n choose 3. Also, let T1, T2 to T sub n choose 3 be indicator random variables corresponding to each of these events. Okay, so we know that whenever we have an event, we can consider an indicator random variable corresponding to that event. And again, as we said last time, again, remember that indicator random variable is defined as, let's say, if the event is A and indicator random variable is X, X of S is defined to be 0 if S does not belong to A, defined to be 1 if S belongs to A. Okay, now for part A, what do we want to do? So for part A, want to consider probability of A1 union A2 union A sub n choose 3. And we want to show that this probability, again, let me show you part A. We want to show that this probability that G of n and P contains at least one triangle is 0 as n goes to infinity in the case that P is much less than 1 over n. So we want to consider P of G of n and P contains at least one triangle means what? Means A1 union A2, right? A1 is the event of having a triangle with vertices 1 to 3, union A2, having triangle with vertices 1 to 4, all the way to the last AI. We want to calculate this and show that this one goes to 0 as n goes to infinity. How can I do that? So by union bound, so one way to bound this from above, of course, is to use union bound. By union bound, P of A1 union A2 A sub n choose 3 is less than equal to P of A1 plus P of A2 P of A sub n choose 3. How much is P of A1? A1 is to have event and to have a triangle with vertices 1, 2, 3. When can I say that I have a triangle with vertices 1, 2, 3? If there is one edge between vertex 1, 2, one edge between 2, 3, one edge between 1, 2, 3, 1, and 3. Each edge appears with probability P. And of course, independent of other edges. So P of A1, that I have one edge from 1 to 2, one edge from 1 to 3, one edge from 2 to 3, is P to power 3. Another P to power 3 for A2, and so on. For the last one also p to power 3. So this is n choose 3 times p to power 3. Okay, see now the problem is reduced to a simple algebraic problem that I want to show that this expression goes to 0 as n goes to infinity. So this goes to, okay, so it remains to show that n choose 3 times p cube goes to 0 as n goes to infinity if p is small o of 1. Now, okay, let's simplify this guy here. So note that n choose 3 times p cube is n times n minus 1 times n minus 2 over 6 times p cube. Okay, now what is my assumption? The assumption is p is small o of 1 over n, which means that limit p over 1 over n as n goes to infinity is 0, i.e. limit pn as n goes to infinity is 0. Okay, so thus limit n choose 3 times pq as n goes to infinity. Let's say that remove this limit for now. This is less than equal to, but this expression is obviously less than equal to n cube, right? This is n, this is less than equal to n, this is less than equal to n. Divide by something will not become bigger for sure. So this is less than equal to n cube times p cube, which is np to power 3. And of course, bigger than equal to 0. Now I can apply squeezing theorem, right? So np, limit np is 0, since limit np and then goes to infinity is 0. Limit np to power 3 as n goes to infinity is also 0. And by squeezing theorem, limit n choose 3 times p cube as n goes to infinity is also 0 as desired. So we did part A. We showed that this upper bound, we want to calculate this limit, show that this probability, show that this probability goes to 0 as n goes to infinity. But we said that this probability is less than this expression. And this expression is same as this one. This one goes to 0 as n goes to infinity. So that means this also, which is less than equal to this, and of course non-negative. So this also goes to 0 as n goes to infinity. Okay, now let's do part B. For part B, the trick is a little bit different. So we want to show that, again, let's go back to part B. Let's look at what we want to do. We want to show that if 1 over n is much less than p, then probability that g of n and p contains at least one triangle is 1 as n goes to infinity. So if you want to show that p contains at least one triangle, I can show that p of, I want to show that p of Sn being positive is 1 as n goes to infinity. And what is Sn? Where Sn is equal to T1 plus T2 all the way to T sub n choose 3. Okay, please remember that T1 is the indicator random variable for A1. A1 means the event that I have one triangle with vertices 1, 2, 3, and so on, all the way to the indicator random variable for A sub n choose 3, which is denoted by T sub n choose 3. So basically T1 is either 0 or 1. It determines whether you have a triangle with vertices 1, 2, 3 or not. Same for T2, same all the way to T sub n choose 3. Now, if I add all these indicator random variables, it measures the number of triangles in total. And I'm denoting this with Sn. So if Sn is 5, for example, that means I am having 5 triangles in total in my random graph. If it's 6, it means I have 6 triangles in total in my random. So here in our context, I don't care whether I have 5 or 6. I just 5 or 6 or 7. I just want to know whether I have at least one triangle or not. So that means I want to know whether Sn, which is the total number of triangles, is positive or it's 0. I want to show that it is positive with probability 1 as n goes to infinity. Therefore, our goal in part B is to show that limit p of Sn bigger than 0 equals 1 as n goes to infinity. Okay, so how do we show that p of Sn bigger than 0 is 1? So to do this, we use the lemma proved last time. And we will show that limit variance Sn divided by expected value Sn squared is 1 as n goes to infinity. Okay, do you remember the lemma we proved last time? Let me show you. Here, this lemma, see? We said if variance xn divided by e of xn as n goes to infinity, e of xn squared as n goes to infinity is 0, then limit p of xn bigger than 0 as n goes to infinity is 1. So our xn here is Sn. So if I show that variance Sn over e of Sn the whole squared as n goes to infinity is 0, that means p of Sn bigger than 0 is 1 as n goes to infinity, which is exactly what I want to do. I want to show that limit p of Sn bigger than 0 is 1. Okay, so going back. Yeah. Okay. Now, okay, let's first find variance Sn. Now, what is variance Sn? Now, variance Sn, what was Sn? T1 plus all the way to T sub n choose 3. Now, we derived the formula last time for variance of sum of random variables, which is variance T1 all the way to variance T sub n choose 3 plus 2 times sigma covariance Ti Tj I less than j. If you remember, this was the formula for variance of sum of random variables. Now, okay, so I have to basically, I'm going to bound. Okay, I want to show that, oh, sorry, this limit of this variance over Sn over e of Sn squared has to be 0. I just showed you the lemma. It says that if this variance over e of Sn squared is 0, then limit p of Sn bigger than 0 is 1. And then goes to infinity. Okay, so I have to show that this limit is 0, I'm going to bound find an upper bound for variance Sn, and then divide by E of Sn squared and do some more manipulation and calculation. So variance Sn, I want to find the upper bound for it. Variance Sn is these terms plus these terms. Now, for the first, I have two groups of terms, variance Ti and covariance Ti Tj. For the first group of terms, variance Ti, what is this? This is expected value Ti squared minus expected value Ti the whole squared, which is of course less than equal to expected value Ti squared. Now, what is expected value Ti squared? Well, each Ti is either 0 or 1, right? So this is 0 times probability that Ti is 0 plus 1 times probability that Ti is 1. So this guy is 0. So this is probability that Ti is 1. And what is the probability that Ti is 1? Ti is one of the indicator random variables. The probability that it's 1, it means the probability that I have a triangle with vertices, which vertices? With either vertices 1 to 3 if it's T1, vertices 1 to 4 if it's T2, and so on. So no matter which three vertices, the probability is anyways P cubed. Probability of having a triangle with any three vertices is P cubed. So no matter whether I'm talking about T1 or T2 or T sub n choose 3, probability that Ti is 1 means probability I have a triangle with three particular vertices, and that's P times P times P, which is P cubed. Well, that's it. So this is so we showed that variance Ti is less than or equal to P cubed. So I found an upper bound for each of the terms appeared in the first group. Now in the second group, I have covariance Ti Tj. Now covariance of two random variables, we saw last time, covariance of two random variables is 0 if those two random variables are independent. Also note covariance Ti Tj is 0 if Ti Tj are independent which would occur if Ti and Tj are indicator random variables for two events I and Aj of having triangles with vertices with two sets of disjoint edges verified. We verified a similar version last time. Last time we showed that if you have two events of having two triangles with two sets of disjoint vertices, then those indicator random variables are independent. But more general than that, we can say that if we have two events of having two triangles with disjoint edges, still the indicator random variables are independent. So when can I say that I have disjoint edges? So if I want to have disjoint edges, of course, one possibility is that I can have disjoint vertices, but another possibility is that I can have, let's say, one vertex in common, and I can still have disjoint edges. So you can verify that as long as you have two events corresponding to having triangle with two sets of disjoint edges, even if there is one common vertex, still those indicator random variables are independent. And if they're independent, the covariance will be 0. Okay, so in this case, covariance is 0, and well, we don't have to do anything. Now, what about the other possibility? If the edges are not disjoint, well, we are talking about triangles, right? So if edges are not disjoint, well, one possibility is that, let's say if you have two edges in common, then the third edge must be automatically common as well, and triangles would be same, and the events would be same as well. And you know that covariance, because I'm talking about covariance terms, right? Remember, we had variance terms and covariance terms. Variance terms are already bounded from above. We are bounding covariance terms. Now, if I have two same events, AI and AI, well, I will have TI and TI, and covariance TI and TI means variance, which is already bounded. So if I have two edges in common, I will have third edge in common automatically, and I will have a variance term, which is already bounded. So the only possibility that is left, if I have no disjoint edges and not two edges in common, then the only possibility is to have one edge in common. So that's the only case that is left to do and to consider to find the upper bound for covariance term. So next, if we consider events AI and AJ for having triangles, two triangles, with one common edge. One common edge means two common vertices. Then covariance Ti, Tj. Okay, let's see how we can find an upper bound for covariance Ti and Tj. In this case, what do I mean by in this case? In the case where Ti and Tj are indicator random variables corresponding to Ai and Aj, which are the events of having triangles with one common edge, which means two common vertices. So in this case, covariance Ti, Tj, by definition is expected value Ti, Tj minus expected value Ti times expected value Tj. Well, now please remember that again, each Ti is an indicator random variable, which means it's a non-negative random variable. So because either 0 or 1, right? And if you have a non-negative random variable, the expected value of it is also non-negative. So this is less than equal to expected value Ti, Tj. Expected value Ti, Tj minus a non-negative number is of course less than equal to expected value Ti, Tj. Now let's see what is expected value Ti, Tj. Well, each Ti and Tj are either 0 or 1. So when I calculate expected value, I have a bunch of 0 terms which have no contribution to expected value. The only term that contributes is if both of them are 1, then Ti times Tj will be also 1, and that is the only term that contributes to expected value. Otherwise, if one of them is 0, it's going to be 0 times something which has no contribution. So 1 times probability that Ti is 1 and Tj, or intersection, Tj is 1. Only if both of them are 1, then Ti times Tj is 1. And I will have a non-zero term. And now what is the probability that Ti and Tj are both 1? So again, please remember, I have two events of having two triangles with one common edge, which means two common vertices. So two common vertices. So instead of 6 vertices in total, I will have 4 vertices in total. And I have to choose one edge. First, I have to choose, if I want to know how many such pair of events I have to first know, first of all, I have to choose 4 vertices out of n vertices. And for that, I have n choose 4 options, right? So this one, n choose 4 option ways to choose 4 vertices. Okay, why 4 vertices? Well, you're talking about two triangles. Normally it should be 6 vertices, but 2 vertices are common, so 4 vertices, and choose 4. And once I choose my 4 vertices, I still can choose the common edge. I have still options for choosing a common edge. How many edges do I have in total? I have 4 vertices, so I can have 6 edges. 4 choose 2, which is 6 edges. So once these vertices are chosen, we have 4 choose 2 equals 6 ways to choose one edge as the common edge. So let's say if I say that this is, for example, my common edge, then I'm going to have this one as one triangle, and let's say this one has another triangle. Okay. So these are the ways for choosing 4 vertices, and this one to choose the common edge. And in total, how many edges should appear here? So 1, 2, 3, 4, 5 edges should appear in total. Again, because 2 triangles means 6 edges, but 1 edge is common, so 5 edges. And each edge appears with probability p. So p to power 5 is the probability of appearing these 2 triangles, for example, with, once I fixed the 4 vertices and once I fix the common edge, then the probability of appearance of 2 such triangles means the probability of appearing 5 edges in total, which happens with probability p to power 5. So once all these are fixed, 2 triangles, i.e. the 5 edges, appear with probability p to power 5. Okay, so this one is basically p to power 5, right? But I also explained, once I fix everything, this is the probability is p to power 5. But how many ways do I have to fix things? Well, there are two things that needs to be fixed. One is the 4 vertices that I will have to choose. And once I fix the 4 vertices, I still have to choose the common edge. And once all these fixed, then the probability is p to power 5 because we are talking about probability of appearance of 5 edges. So thus, what can we say? Now let's look. Variance Sn is less than or equal to, okay, let's look at the expression we had for variance Sn. It's bunch of variance terms and bunch of covariance terms. Each variance term was bounded above by p to power 3. How many such terms do I have? N choose 3 such terms. So n choose 3 times p to power 3. N choose 3 times p to power 3 plus bunch of covariance terms, right? Where is bunch of covariance term, 2 times. Now each of these covariance terms resides bounded above by p to power 5. How many such terms do I have? N choose 4 times 6. And there is 2 outside of the bracket. It was 2 times sigma covariance, right? So 2 times n choose 4 times 6. And each of, once everything is fixed, we said that p to power 5 is the upper bound. So this is n choose 3 times p to power 3 plus 12 n choose 4 p to power 5. Okay, and this one you can easily see that this is less than or equal to n cubed times p cubed plus n to power 4 times p to power 5. Well, obviously n choose 3 is less than or equal to n cubed. Just write the expression n times n minus 1 times n minus 2 over 6, which is of course less than or equal to n cubed. N choose 4, again write the expression times 12. You can easily see it's less than or equal to n to power 4. Hence, variance, okay. What do we need? Variance Sn over expected value Sn, the whole squared. The variance Sn, we already found the bound for it. What about the expected value Sn, by the way? Expected value Sn, what was Sn? It was T1 plus T2 all the way to T and choose 3. And expected value is a linear function, so I can write it as expected value T1 plus expected value T2. Now each of expected value Ti's, again remember each Ti is either 0 or 1. So 0 times something does not contribute. For each Ti, expected value Ti is 0 times something, which vanishes, plus 1 times P of Ti equals 1. And how much is P of Ti equals 1? The probability that, once you fix your set of vertices, the probability that you have a triangle there is P to power 3. So this is P to power 3, and how many such terms do I have? N choose 3 terms. Because expected value Ti is equal to 1 times probability that Ti is 1, and the probability that, once I fix the set of my vertices for 3 particular vertices, the probability that I have a triangle there is the probability that all 3 edges appear. Each one probability P, so it's P to power 3. So for each Ti, E of Ti is P to power 3. E of T1 is P to power 3. E of t1 is p to the power 3, E of t2 is p to the power 3, last one is p to the power 3. How many such terms do I have? N choose 3. So n choose 3 times p to the power 3 is the denominator. So this is less than or equal to, numerator was less than or equal to n to the power 3 times p cubed, n to the power 4 times p to the power 5 divided by n choose 3 times p to the power 3. And lastly, therefore, variance Sn divided by expected value Sn the whole square is less, you can say that is equal to O, right? The big O of, let me write, expression one more time, n to the power 3, p to the power 3 plus n to the power 4, p to the power 5 divided by n choose 3 to the power 2 times, oh no, yes, there is a power 2 here, choose 3 to the power 2 times p to the power 6, which is O, big O. Now p to the power 3 over p to the power 6 is 1 over p cubed. Now n cubed over, well, n choose 3, you can easily show that 1 over n choose 3 is O 1 over n cubed. To power 2 is 1 over n to the power 6. So n to the power 3 over n to the power 6 is 1 over n to the power 3. So it's going to be 1 over n to the power 3 p to the power 3 plus n to the power 4 over n to the power 6 is 1 over n squared. So 1 over n squared p. So you just need to check that basically n cube over n choose 3 to the power 2 is O 1 over n cube. And this makes sense, right? N choose 3 means what? N times n minus 1 times n minus 2 over 6. So it behaves like n cube. So n cube over, now, this term I just said that behaves like n cube. 2 power 2 behaves like n to the power 6. N cube over that behaves like 1 over n cube. And of course, once you check that, you can similarly check that n to the power 4 over n choose 3 to the power 2 or 1 over n squared. Okay, now what was our assumption here in part B? Remember, what are we doing? We are trying to prove this, that if 1 over n is much less than p, this limit is 1. We said that we will do this by checking that the limit variance over expected value squared is 0, right? See? Yeah. We want to show this. To do this, we use the lemma that limit variance over expected value squared is 0. So I just need to show that this guy is 0. So far, we showed that this is less than equal to, or it's actually big O of this guy. So if this guy is 0, this guy is 0, we are done, because then that means this guy is 0. Okay. Now, why is this guy 0? Again, what was the assumption? 1 over n is much less than p in part B. So let me write down the assumption again. Assumption, recall. Assumption was 1 over n was much less than p, i.e. limit 1 over n divided by p. Of course, p, I mean p of n, right? It's a function of n. 0, i.e. limit np, right? 1 over np is 0. So limit 1 over np is 0. So this guy is 0, this guy is 0 too. Limit 1 over np to power 3 0, which is this term here. And the second term, 1 over n squared p, and limit 1 over n squared p, which I can write it as limit 1 over np times limit 1 over n. This is also 0. This means limit variance Sn over expected value Sn squared and goes to infinity is 0. And that means limit p of Sn bigger than 0 as n goes to infinity is 1. Sn bigger than 0. Limit p of Sn bigger than 0 is 1 as n goes to infinity as desired. So we showed that 1 over n behaves like a threshold function if the random graph g of n and p is much less than that, the random graph would contain no triangle asymptotically almost surely, and if p is much bigger than that, or in other words 1 over n is much less than p, then the random graph g of n and p would contain at least one triangle asymptotically almost surely.